Here's your video for solving exponential equations. Let's start with this property of equality for exponents. If a to the x equals a to the y, then x must equal y, and a, the base, must be positive and it cannot equal 1. And going the opposite direction is true. If we start with some equation x equals y, then we could have on both sides of the equation the same base with x and y as the exponents, and we will be guaranteed to have another true equation. These properties show themselves in an example like 5 to the x equals 5 to the third. We've got an exponential equation, or an exponential expression here on the left side because our variable is up in the exponent, and it is an exponential equation. And our property will tell us, since we have a base 5 on both sides, the exponents must be equal. X equals 3. And once we establish x equals 3, I can make both of these become exponents with any base, and I'll still have a true equation, just as long as the base is a positive number that is not 1. Some other quick examples that show this property: 3 to the power of 2x minus 1 equals 3 to the power of 8. Again, base 3 on both sides, so it is valid for us to just pull down these exponents. 2x minus 1 must equal 8. And now we have a way to solve this equation. It's a linear, so we'll just isolate x equals 9 over 2, and that's the solution to our original exponential equation. One more quick example: 2 to the power of x equals 8. Now currently we don't see the same base on both sides, but if I know that 8 can be written as 2 to the power of 3, now I'm able to utilize this property. Base of 2 on both sides, so the exponents must be equal. X equals 3. So let's take a look at another example like this, where we're going to start with an equation and aim to get the same base on both sides of the equation, and then we can set the two exponents equal to each other. Here's that example. You could pause the video right now and try this one, and then restart, and we'll look through the answer together. Seeing a base of 2 on the left side, I'm interested in looking at the right side and coming up with, how can I write 16 as 2 to some power? Well, we just saw 2 to the third was 8, and 2 to the fourth equals 16. Now that we have base 2 on both sides, we can set the two exponents equal to each other. 3x minus 1 equals 4, and then we'll solve this equation. X equals 5 over 3. Our next example will be solved the same way, but we have to remember how to handle fractions related to exponents. We see a base 3 on the left, so we're interested in coming up with another expression using base 3 for our number on the right side, 1 over 81. Let's first just deal with the 81. Do we have 3 to some power to equal 81? And it is 3 to the fourth. The next thing I want to do is remember that I can use a negative exponent to represent a reciprocal. So 1 over 3 to the 4 would be the same as 3 to the power of negative 4. So when I see fractions in this type of a problem, I know I'll need to use a negative exponent. And I would first just focus on the denominator, come up with 3 to what power equals 81, and then reciprocal to give it that negative exponent, and no more fraction. Now we can wrap up by setting these two exponents equal to each other. X equals negative 5 over 2. Here's another example for you to try. Pause the video, work through this one, and then restart. We'll go through the steps of the answer. We have a base of 5 on the left side of this equation. I'm looking at the right side to come up with an exponential expression also using base 5. I know that the 25 is 5 to the second power, so 1 over 5 to the second would be 5 to the power of negative 2. So 25 is 5 to the power of positive 2, but since it is in the denominator, we're using 5 to the power of negative 2. And again, we're going to setting the two exponents equal to each other. Another linear equation to solve. Bring in the 3 over, make a negative 3, with the negative 2 makes the negative 5. And then x equals negative 10. And to clear out this fraction, I chose multiply both sides by 2, or basically the reciprocal of this coefficient. So there can be a clear path through these equations when we see a way to set up both sides of the equation using the same base. But what if we had an equation that did not set us up to handle it that way? For example, 2 to the power of x minus 3 equals 15. We don't have a way to figure out 2 to what power equals 15. Well, it's not an integer, it's not a rational number. It's a question that really can only be answered using logs. 15 would be 2 to what power? Well, that number would be log base 2 of 15. And remember, this is a relationship that we know about between exponential equations and log equations. If we're interested in coming up with an exponent, then I would do a log using this base, in this case it's 2, a log base 2 of 15, and that answer is the exponent needed. 2 to that power would equal 15. Well, before we get to examples where we utilize logs heavily, let's do a few more examples where we can try to set up the same base on both sides. Our next example, 3 to the power of x squared minus x equals 9. I can set up the 9 using a base 3, 3 to the power of 2. Now we're pulling down those exponents. X squared minus x equals positive 2. Well, now we're looking at a quadratic, so I'm going back to my methods for solving quadratic equations. I'll bring all my terms over to the left side. X squared minus x minus 2 equals 0. This quadratic we can factor x minus 2 times x plus 1. And solving will give us x equals positive 2 and x equals negative 1. We can check each of these answers. Up here in the exponent, 2 squared is 4 minus 2, so we would see 3 to the power of 2 equals 9. And if x was negative 1 squared would be positive 1. Positive 1 minus a negative 1, so there's another 1 plus 1 equals 2. And again, 3 to the power of 2 equals 9. So we have two solutions to this exponential equation. Here's our next interesting example, and what jumps out to me is that each of the bases can be written using a base 2 if I make some adjustments. So we'll go through this positive 4 I know is 2 to the second power, and I'll just carry down the exponent of x squared. This factor right here, 2 to the power of 9x, is good as is. It has that base 2. Now over here, 1 over 16, we even saw one of these earlier. 16 is 2 to the power of positive 4, so 1 over 16, 2 to the power of negative 4. Now thinking back to our property, we really only saw one base on each side, and here we have two factors, which is stopping me from trying to use that property right now. I should come up with a way to simplify this expression, which you can do because we have the same base. Let's first deal with what we see here. An exponent outside of parentheses, the rule for exponents there is we multiply exponents. So we can simplify this part as 2 to the power of 2x squared. I'll bring down times 2 to the power of 9x equals 2 to the power of negative 4. Next, I can put together these two parts using another rule for exponents, the one where if I saw x to the third times x to the fourth, I'd know that's x to the seventh. If we multiply factors with the same base, we'll add up the exponents. Now in this case, our exponents are not like terms. I'll still try to set them up with an addition, but this is really the best I can do. Keep that base of 2, and adding my exponents would give me 2x squared plus 9x. But that is good enough for us to use that property. Now we have a base of 2 on each side, only there once, so we can take these exponents and set them equal to each other. Now it's looking like another quadratic, so I'll put it into standard form. And it's another quadratic that can be factored. 2x plus 1 times x plus 4 leads us to these solutions. X equals negative 1/2 and x equals negative 4. And if you're thinking at this point, can we use quadratic formula? Absolutely. Once we get to this quadratic equation, we can solve it any way that we want. I happen to spot that it could be factored, so I went that route. If I couldn't factor it, or if I just didn't feel like trying to factor it, I would go right to quadratic formula for the solutions. Now let's get ready to handle those types of equations where we just could not see a way to get the same base on both sides of the equation. We'll need to use another property. This one, we see logs play more of a role. If s equals t, so we have some equation, both sides are equal, then log base a of s equals log base a of t. Basically, it's saying if you have an equation, you can do a log to both sides of the equation and still maintain equality. So it's almost like we're developing rules similar to you can add the same thing to both sides of an equation, you can subtract from both sides of an equation as you're solving, multiply as long as it's same thing both sides, divide we can do. Now we have rules incorporating how we can use exponents on both sides of an equation, and this property says we can do a log to both sides of an equation, just as long as we're using the same base. And it works the opposite direction. If we're looking at two logs that are equal using the same base, we can drop those logs and we're left with another valid equation, s equals t. And to handle the technical aspects, s and t both have to be positive. We don't do logs of negative numbers, and our base has to be a positive number that is not 1. So going back to our example, 2 to the power of x equals 15, either we remember how we can rearrange these terms to set up a log equation, so this would be log base 2 of 15 equals x. That's a fine way to go. But when the problems get a little bit more complicated, it seems, in my opinion, to work out more smoothly if I think I'm going to do a log to both sides. So the way that would look in this case, we have even some options when it comes to using logs. I could just choose to do a log base 10 on both sides. What will follow right after that move is knowing about a property of logs, that the exponent that is here in our argument of this log function, the exponent we see, we can move it out front of the log. So log of 2 to the power of x is going to equal x times log of 2 with no exponent. So the exponent we see, we move it out front in a multiply, x times log 2, and this is a base 10. If we don't see the base, we assume it is a 10, equals log 15. Haven't changed the right side yet. And to finish solving for x, since I have x times log 2, I can divide both sides by log 2. And we're left with x equals log 15 over log 2. How do we account for the fact that we have two different looking answers? Think about if we had to come up with a decimal approximation for log base 2 of 15. A calculator, at least the ones I use, don't let me do a log base 2. I can do a log base 10, or I can do a log base e, usually called natural log. But to do a base 2, I'll have to use the change of base formula, which tells us that this equals a fraction, log 15 over log 2. And this is a base 10 log. It's going to give us the same answer if we use natural logs, but same type of log in numerator and denominator. So I'm just going for base 10 log, so I can show you that these two answers really are exactly the same. One last thing I would like to point out is that we often choose the base of our log depending on the base that we see. So since this is a base 2, I might want to choose to do a log base 2 on both sides. Now again, what we have on the left side, we can either see this exponent x we're going to bring down, and then log base 2 of 2. We should recognize those situations where our base and our number in the log function, the argument, if they are the same, think about, well, this is 2 to what power equals 2. Still, that would have to be 1. So, or you know the log property that when our base is the same as this argument, it basically gets simplified to equal just this exponent. And that really is because we have moved this exponent out front, and now we're doing an x times 1, or just x. And there we see the log base 2 of 15. So we have a few different ways we can handle these equations. I'm going to primarily use a base 10 log on both sides. But as we get to other examples, we might see some occasions where we would be interested in using a log with a specific base that matches up with the base that we see in the exponential expression. And lastly, if I was doing a decimal approximation, again, I'd have to use change of base, and I could choose to use natural log. We will get the same decimal answer for each of these three fractions. Of course, for these two, they're identical, and natural log, the ratio of natural logs, will give us the same results. So let's keep going with this idea using a similar but a slightly more complicated example where our exponent now has two terms. One thing I definitely want to observe is the variable is up in the exponent, and when the variable is in the exponent, usually we will need to use logs to solve the equation. So I will do a log both sides. I'm going with base 10 log. On the left, I'm going to take this exponent, x minus 3, and bring it out front. But since it's two terms, I'm really cautious. I'll have it in parentheses. Here's the x minus 3 times log 2, and on the right side we have the log 15. So it's the exact same move, taking the exponent, putting it out front, but since it's two terms, I'm extra cautious, and I have it in parentheses. That will be critical for those times when we'll need to do some distributing as we solve the equation. Now I'm working to get the x by itself, solve for x, so I think I will choose to do divide both sides by log 2. That will leave us with the x minus 3. On the right side, I'm setting up this fraction, log 15, over log 2. So just did divide both sides by log 2, and one last move to solve for x, adding 3 to both sides. X equals log 15 over log 2, that entire fraction plus 3. Punching it into the calculator, I'm coming up with a decimal approximation of 6.9069. Now a different choice would have been to use a log base 2. Let's just take a quick look at how that would show as a solution. Log base 2 of both sides. Now on the left I'm doing a couple things, just bringing down the x minus 3. It's basically, I'm still bringing it out front like I did on this example, but I'm also at the same time saying log base 2 of 2 equals 1. So I'm left with just x minus 3 times 1, or x minus 3. Here's the log base 2 of 15 on the right side, and I'm simply adding 3 to both sides here. X equals log base 2 of 15 plus 3. And just like this example here, if I needed to do a decimal approximation, I'd have to do a change of base right here, and I'd be coming up with x equals log 15 over log 2 plus 3. For our next example, 5 to the power of x minus 2 equals 3 to the power of 2x plus 1. Now it doesn't fit the pattern that we're used to in terms of rearranging to come up with a log equation. So I really have to think do log to both sides of this equation. I see a base 5 on the left, a base 3 on the right. I could do some things by choosing a log base 5 or a log base 3. We hopefully are seeing that we can come up with multiple answers that are all numerically equivalent. They just look different based on different log bases that we're using. So I'm going with base 10 log. And I've made two moves in this step. I brought the exponent out front. Both of them had two terms. Both exponents had two terms, so they're both in sets of parentheses. Here's my x minus 2 times log 5. On the right, 2x plus 1 times log 3. Now there are going to be some specific steps for us to solve for x, because we see x terms showing up in two places. What we'll have to do is distribute out, and what we're seeing here is these two terms, x and negative 2, are both multiplied by log 5. So distributing a log 5 to each of these terms gives us x times log 5 minus 2 log 5. It is this log that we're multiplying to each of these two terms in parentheses. We'll do the same thing on the right side, 2x log 3 plus 1 log 3, and I've left that coefficient of 1 out. Next step is to collect our terms with x on one side. I'll bring this 2x log 3 over to the left side. I have x log 5 minus 2x log 3, and I'm moving this negative 2 log 5 over to the right side. So we have log 3 plus 2 log 5. Once we have our terms with the x collected on one side, the next move is to factor the x out as a common factor. We're looking still really only at two terms, so I can divide an x out from this term, and I can divide an x out from this term. We'll be left with log 5 minus 2 log 3. The x we divided out, it's the common factor that is now out in front of the parentheses. There's no factoring for us to do on the right side. This was really just a step to help isolate x. It's a way that we can get our x from being in two separate terms into just showing up once. And the last move would be to isolate this x, divide out this entire expression. So x equals our right side log 3 plus 2 log 5 up in the numerator, and after we're dividing both sides by log 5 minus 2 log 3, that's showing up in our denominator, log 5 minus 2 log 3. One advantage of using base 10 logs on both sides when we started the equation is that we won't need to do a change of base here. All of our logs are currently in base 10. So if we're coming up with a decimal approximation, it's a little bit easier if we start out just using those base 10 logs. Here's our next example. It's going to require some similar steps, but it will have a little twist at the end. So you could pause the video and give this one a try, then restart, and we'll look at the answer together. On the left, a base 10, on the right, base 5. We don't have a way to adjust these sides so that they're using the same base. It's not like we have a base 5 and a base 25. So we'll need to use logs. I'm going to just go with a base 10 log, and the fact that we have a base 10 here I think is just going to help with the simplifying a little bit along the way. So a base 10 log both sides, and it will cancel this base 10 right here. We should have only a negative 2x left on the left side. On the right side we have the exponent moved out front, 4x is out front, and there's the log 5. So we're doing a base 10 log both sides. We're moving our exponents to the front, and here we had a log 10, a log base 10 of 10, which equals 1. So the negative 2x times 1, just leave it as negative 2x. Next we need to collect our terms with x together on one side. We've got one large term here on the right, 4x log 5. If you're thinking about dividing both sides by x, we should avoid that always when solving equations. I would never want to divide both sides of an equation by a variable or any expression that has a variable, because it's possible that we're dividing by 0. So we avoid dividing by negatives. What we'll do instead is collect all those terms on one side and factor the GCF out. So I'm moving my negative 2x over to the right side. I have 0 equals 4x log 5 plus 2x. Now I'm going to factor the x out as a GCF. I could factor out, I shouldn't even say GCF because the greatest one would have us also use the 2. But I'm mostly interested in isolating that x. So I've only brought out the factor x. I've left other common factors like positive 2 in the parentheses. Just want to get that x by itself. Now at this point we can look at it two ways. I could look at it like I'm solving by factoring, and in that case this x would lead us to a solution of x equals 0. And this setting this equal to 0 won't lead us to any solution. There's no variable in this expression in parentheses. So we're left with just one solution, x equals 0. The other way to look at this would be to divide both sides by this big expression in parentheses. And that would be okay because no variable in here. It's just another number. It's an irrational number, but we can divide both sides of an equation by a number. And that's another way that we would be left with x equals 0. Here's a similar example, and also it's about time we start seeing a base e. You could pause the video and try this using similar steps here. I would tell you that when we do see base e, that's a clue to just go ahead and use natural log. If I see only numbers here, then I would choose a base 10 log if I don't see the e. But if I see the e, I'm choosing natural log. So if you work through this one, use natural log. And now let's look at the solution. Natural log to both sides. It is just another type of log. It's a log base e, so we're doing all the same steps. I'm taking my exponents, moving them out front. On the left side, I'll have x times natural log 3. On the right side, we have the base matching up with the argument, natural log e. So those, we can think of them kind of sort of like they're canceling, but we're really doing a negative x times 1, left with just negative x. We're going to wrap this up by again getting our terms with x together on one side. I'll choose the left side. Factoring the x out as a common factor, we're left with natural log 3 plus 1 in parentheses. And it's the same conclusion as what we saw here, that we have only one solution at x equals 0. Now let's look at a couple more examples where we're using a base of e. And these are some examples that show up pretty frequently in equations that we'll see in the near future. I can think the same way I've been thinking so far, just that when I see base e, I will choose to use a natural log. This example on the left, it's ready for natural log both sides. On the left side, we're bringing down the exponent 0.03x, and natural log e is 1, so we have that vanish. On the right side, there's the natural log of 2.5. Finish solving for x. We have x times 0.03. Let's divide both sides by 0.03, and there is our exact answer. If I want exact, I'm leaving it just like this. If I want a decimal approximation, then I'll punch in and get approximately 0.3054. Our example on the right, there's something that tells me I'm not quite ready to do the natural log, and it's this 30 multiplied to our exponential part. I would like to do a natural log only when I see e and the exponent, and no number out front. So I'm going to divide both sides by 30. I don't want to do any rounding, so I'm keeping the fraction 1/6. And on the right side, we're left with e to the power of negative 0.12x. Divided out that 30. Now we're ready for the natural log both sides. On the left, we'll have natural log of 1/6. On the right, we're bringing our exponent down, and natural log of e equals 1. Multiplied by 1, it's gone. Finish solving for x. We'll divide both sides by a negative 0.12. There's our exact answer. The decimal approximation about 14.9313. Here's an example that is a little bit tricky. It requires us first making a very clear observation about what terms we see. I see e to the power of x as well as e to the power of negative x. And additionally, there is a third term. We don't always see that, but what really catches my eye is a term with e to the power of positive x and e to the power of negative x. When I see problems like this, it requires specific steps, which are, first, let's understand e to the negative x. Just like our negative exponents earlier, it's indicating a fraction. So I could write this equation, 2e to the x equals 1 plus 3 over e to the x. Now careful that we're going to leave the 3 in the numerator. Only we're moving the terms that have, or the factors that have, a negative exponent. So e to the negative x, we're moving to the denominator, making it e to the positive x, but this coefficient 3 does not move. It stays in the numerator. Now I'm thinking about handling equations that have fractions, and I like to multiply every term by the common denominator. In this case, we have only one denominator, e to the x. I'm multiplying every term in this equation by e to the x, and absolutely it must be every term on both sides. What's happening when we multiply 2e to the x times another e to the x? Well, let's just think about e to the x times e to the x. The rule that's at work here is this rule about exponents. What happens when we multiply exponential expressions that have the same base? We add the exponents. This is just like our x to the third times x to the fourth equals x to the seventh. Just add those exponents. So we know this multiplication will still have a base e. We need to add x plus x. So just think 1x plus 1x equals 2x. So e to the x times another e to the x gives us e to the 2x. So our multiplication to this term gives us 2e to the 2x equals e to the x times 1, just e to the x. And here is the fraction where our denominator is canceled out. We're left with just the plus 3. Now, the equation that we're left with has a quadratic form. I'll move all the terms over to the left side so I can keep a positive leading coefficient. And it's a substitution that we'll need to see an actual quadratic. In place of e to the x, we'll use a u. And if I square both sides, I get a good rule. U squared can be used in place of e to the power of 2x. So all these moves that I've done so far, I know to do these rules only because I've seen this type enough to know that these are the required steps. I see e to the power of positive x and e to the power of negative x. So my first thought is, let me put that in the denominator, follow up with what I like to do with equations with fractions, multiply everything by e to the x. Know that my result is probably going to be a quadratic. That just happens in equations like these. So I'm setting all my terms over to one side equal to 0. I know I'm going to end up needing to do a substitution to see a quadratic. It's going to be u in place of e to the x. Let's look at this quadratic. 2u squared minus u minus 3. Now factoring it, I spotted that this one could be factored with grouping. If I didn't see it, I would go right to quadratic formula to find u. But in this case, I see some factors. U plus 1 times 2u minus 3 equals 0. So we have solutions u equals negative 1, u equals 3 over 2. It's a common place to stop right here, but let's not do that. We want to solve for x, so let's back substitute, get our e to the x back in place of u. And we're very close to the end. There are lots of interesting and different steps going on, but we do these steps consistently with this type of problem. So it's a little bit challenging at first, but I think it's not too terrible in terms of understanding the flow through these problems. The same basic steps are occurring from start to finish for each of the problems of this type. So what we have to do now to wrap it up, solving for x, it looks like we're going to need to do natural log both sides, just like those simpler e to the x equations we saw. Our equation on the left, e to the x equals negative 1. Natural log both sides. On the left, we'll be left with just x. On the right, we're doing natural log of negative 1, and that must be eliminated immediately. We do not do logs of any negative numbers. So there's an extraneous answer, natural log of negative 1. You can even punch it into your calculator to see that it's not going to give us some value that we want to try to use. So that one's tossed out. No logs of negatives. This side, we're going to be okay. We can do a natural log both sides. And we have our solution, x equals natural log of 3 over 2. As a decimal approximation, x is approximately 0.4055. So before we move on, just one last remark. I know that these are the required steps just because of what I see initially about this equation. And I think the biggest clue would be we see a term that has e to the x and a term with e to the negative x. If I'm going to see that, I'm going to assume that these are the steps that I'll follow to get to my answer. One last interesting example. We'll explore a couple of ways that we could work through this problem. I'm first going to try to write my exponential expressions using the same base. The 100, I know I won't be able to get that as 5 to some power, but it's okay for the moment because there's no x up in the exponent. Here's 5 to the power of x. I'll do some work on the 25. I know 25 is 5 to the second. I'm bringing down the exponent, and right away I'll be multiplying those exponents. Let me just bring down the right side first. Now let's simplify a little by multiplying our exponents. Careful that we will have to distribute, so it's 5 to the power of 2x minus 4 equals 100 times 5 to the x. Now I caution you, if you thought about could we multiply the 100 times 5, and I want you to get rid of that thought right away. It's a bad move because it breaks order of operations. We have to do exponents first. So as long as our x is unknown, we cannot do 5 to that power, so the times 100 is off limits altogether. With many of the examples and equations that we've worked in our lives up to this point, we're used to really just dealing with multiplying, dividing, adding, and subtracting. So we know we can do the multiplying and dividing first. We get accustomed to when we spot some multiplication, we just go ahead and do it. But with our equations now that are using many more exponents and logs, we have to be cautious and understand that those operations are taken care of first, and until that happens, we have to avoid multiplying some number to the base of an exponential expression. So no 500 to the power of x here. What we'll do instead is think about collecting our terms with x on the same side. This is a 100 times 5 to the power of x. I'll divide both sides by 5 to the power of x. And now my terms with x are all on the left side. On the right side, those exponential expressions cancel. We're left with 100. What has occurred on the left side here? It's a rule about when we divide exponential expressions that have the same base. We had a few examples where we multiplied, and if there was the same base, we would add up the exponents, so that when we do a divide, we subtract the exponents. So 2x minus 4 minus x, the 2x minus x is leaving us with that x right there, and bringing down the constant minus 4. So what we see here is a result of subtracting our exponents, because we're dividing them and they both have the same base. Keep that same base and subtract the exponents. So it's a nicer looking exponential equation now. I see the variable up in the exponent, so I know I'm going to need to do some logs. I'll choose a base 10 log both sides. On the left, the exponent x minus 4 I've brought down. I have it times log 5. What about on the right side? It is log 100, but I ought to take care of that pretty quickly. The base is 10, and our 100 is 10 to the power of 2. So log base 10 of 100 equals 2. We should simplify things like that as soon as we see them. So some more steps to finish solving for x. I will choose to divide both sides by log 5. It's leaving us with just the x minus 4 on the left side. On the right side, 2 over log 5. And now add 4 to both sides. X equals 2 over log 5 plus 4. There's a solution. Let's talk about a slightly different approach I could have used at this point right here, something that we've seen in some earlier examples where we did a distribute. So I could choose to do that also. Log 5 times x and log 5 times negative 4. Distributed looks like x log 5 minus 4 log 5 equals 2. Now more moves to isolate the variable x. Let's get rid of this term. Add 4 log 5 to both sides. And now divide both sides by log 5. We're left with this expression. How do we account for two different looking answers? We could do it a couple of different ways. We could do some decimal approximations and see that we get the same irrational number. At least it's the same out to the 9 digits or however many decimal places we can see on the calculator. We could also show algebraically that they are equal. So let's do that pretty quickly. We're going to take this fraction right here, and I'll split it up into two fractions. I'm splitting up the numerator into two fractions. Each one is using log 5. So we have 2 over log 5 plus 4 log 5 over log 5. And there we'll have the factors of log 5 cancel, and we see our 2 over log 5 plus 4. Exactly what we had here. But before we wrap this problem up altogether, I do want to look at yet another option we have for solving this equation. And the reason is that when it comes to working with logs, we tend to see many, many different paths and different looking answers through problems. So you should be aware that two answers may not look the same, but could actually be numerically equivalent. And also, what's most important is learning the main techniques that we have so that you're not forced into a specific set of steps to solve a problem. You've got some different options at your disposal. So the other option I saw would be to do a log right here at the beginning. I can do it because I have just one term on each side. So I'll do log base 10, and I just make sure I'm doing log to everything, just once per side. On the left side, I know how this plays out. I'm bringing down the exponent x minus 2 times log 25. On the right side, I'm going to apply another property of logs, the one that says if we have a product in our argument, we can split this up into two separate logs. I'm seeing a 100 times 5 to the x. I can split it up as log 100 plus log 5 to the x. That's a property of logs. When we see a product in here, a multiplication, we can split it up into two separate logs using an addition. Now some more moves. The left side I'm going to keep it as is for now. The right side, a log 100, make that into the 2. This log 5 to the x, bring the x out front, that exponent bring it down. Now I see terms with x in different places. I'll need to multiply out, distribute, and collect terms with x on the same side. On the left, distribute the log 25. I got x log 25 minus 2 log 25. Right side is the same, no change yet. Now I'll bring my x log 5 over to the left side, so x log 25 minus x log 5. This term right here, the negative 2 log 25, bringing that to the right side, 2 plus 2 log 25. Now to continue solving for x, I'm factoring it out as a common factor with log 25 minus log 5 in parentheses. And now I'll divide this expression from both sides and get x equals, our right side is the numerator, 2 plus 2 log 25, denominator, log 25 minus log 5, what we divided out from the left side. So there's an answer. It's even different from the 2 that we found a little bit earlier. Numerically, it is the same. It's approximately that 6.8416-ish number, whatever those digits were. Let's do some steps algebraically to try to show an exact match to our earlier solution. So I think first what I'll choose to do is the log 25s, write those as 5 to the second power. And I'll do that because now those exponents, I can bring them out front. The 2 here in the denominator I'm bringing out front. This 2 I'm bringing out front. There's a 2 already there, so I'll have to multiply. It's going to create 2 plus 4 log 5 up in the numerator. In the denominator, 2 log 5 minus log 5. Next, in the denominator, we actually have, you could think of them as like terms. A 2 log 5 minus 1 log 5 equals 1 log 5 left in the denominator. Absolutely, we can subtract. They both have the same factor log 5, so we could think of 2 and negative 1 as the coefficients, leaving us with 1 log 5. Here's the exact answer we saw. The second time, I could split it up into separate fractions to see the actual 2 over log 5 plus 4, and there's that decimal approximation, approximately 6.8614.